Multivibrator is a pulse generator circuit having two output states and transition from one state to other may be automatic or user driven, meaning that by means of external trigger pulse or combination of both based on transition of states. Multivibrators are classified as Astable multivibrator or free running multivibrator. This requires no external trigger pulse, signal or pulse. That means it is transition is automatic. Number 2, monostable multivibrator or one shot multivibrator. This requires one external trigger signal and other one is automatic. That means it is a combination of both automatic and user driven. Number 3, bistable multivibrator or flip-flop. This requires two external trigger signals and both states are stable unless and until trigger pulse is applied. State change state transition does not take place. Here one state is stable and other is quasi stable. That means for transition from one state or the stable state to the other state needs external signal, and thereafter it once again returns to its stable state after some time. And as stable multivibrator, both states are quasi stable. Quasi stable means not stable. The state remains high for a certain period of time. Transistor based Astable multivibrator. Here two similar transistors T1 and T2 are connected from a common VCC supply with two load resistance RL1 and RL2, two base resistance RB1 and RB2, and coupling capacitor C1 and C2. In this way, this is output of transistor T1 VC1 equal to Q bar, and this is output of T2 equal to VC2 equal to Q. This is the construction of an astable multivibrator. Now operation. This circuit requires no external trigger signals. How does the circuit works? Here two transistors T1 and T2 are identical. For symmetrical waveform, we may have RL1 equal to RL2, RB1 equal to RB2, and C1 equal to C2. When supply is switched on, both capacitor C1 and C2 starts charging through RL2 and base of T1 for transistor T1, and for transistor T2 through RL1 and base of transistor T2 with the polarity as marked here. Now, though T1 and T2 are similar transistor, still they will have some parameter mismatch. That means whatever precautions may be taken, two exact similar transistor cannot be manufactured. They will have some differences in terms of current gain, beta 1 and beta 2, where beta 1 is the current gain of transistor T1 and beta 2 is the current gain of transistor T2. A part of base current will also be supplied by the VCC through RB1 for transistor T1 and RB2 for transistor T2. So initially base current for transistor T1 is the combination of charging current of capacitor C1 and base current through RB1, and base current of T2 is the sum of charging current through capacitor C2 plus base current through RB2. Now, due to transistor parameter mismatch, one of the transistor will generate more collector current, because we know that VCE of a transistor is given by VCC minus ICRL, where IC equal to beta IB. For transistor T1, this equation will be like this one: VC1 equal to VCC minus IC1 RL1, and for transistor T2 it would be equal to VC2 equal to VCC minus IC2 RL2. Equal to VCC minus beta 1 IB1 RL1 and equal to VCC minus beta 2 IB2 RL2. Due to transistor parameter mismatch, suppose beta 1 is greater than beta 2, then obviously is IC1 will be more than collector current of transistor T2, that is IC2, and hence voltage drop VC1 will be less than VC2. That means this voltage will be VC1 will be less than VC2. As the voltage of transistor T1 is more less than VC2, hence further increase of base current of T1 will be more than T2. Why? Because when this voltage falls, charging current also through capacitor C2 falls. Therefore, IB1, that is equal to IC1 plus IRB1 and IB2, that is equal to IC2 plus IRB2 will make a difference. How? Because now IC2 is less than IC1. So in a cumulative process, further IC2 will decrease and IC1 will increase, and within a very short time it will be seen that T1 gets turned on and forcing T2 to go into cutoff. T1 will be turned on while T2 will be forced to go into cutoff. Two transistors at the initial stage of switching on to the supply will make a race, and in the process one transistor will be successful to make itself turned on while the other will fail and go into off state. Let us consider that T1 turns on first. T1 turns on first and T2 is cut off at that time. Since T1 is turned on, therefore Q bar equal to 0, because VC1 equal to 0 and Q equal to 1, because VC2 equal to plus VCC. When T1 turns on, C1 gets completely charged up to a voltage. C1 charges up to plus VCC with the polarity as shown in figure, while C2 fails to continue charging. But as soon as T1 turns on, C2 starts discharging in this way, because this path then becomes short circuit. T1 behaves like a short circuit. So C2 discharges to starts discharging through RB2 T1 and VCC. As soon as C2 completely discharges, it tends to charge with opposite polarity. After complete discharge, C2 will start charging with opposite polarity. When C2 starts charging with opposite polarity and voltage across C2, that is equal to VC2 VCC cap 2 increases just above 0, a positive spike will be applied across base of T2. A positive spike will be applied across base of T2. On the other hand, C1 will stop charging, because at that time C1 will be charged up to plus VCC. So due to this positive spike, base current of T2, that means IB2, now will be more than IB1. Why? Because now IC1 charging current has stopped or decreased to 0, because it has charged completely and no charging current is flowing now. Only a base current is passing through RB1 for transistor T1. And on the other hand, as C2 charges with opposite polarity, base current of IB2 will be more than IB1. Now T2 will force T1 to go into cutoff, and T2 will be turned on. Under this situation, T1 will be off and T2 will be on. Consequently, VC1 will be equal to plus VCC, that is equal to Q bar equal to 1, and VC2 will be equal to 0, that is equal to Q. Just states have changed their sequence. That means transition has been taken place. Transition of state has been taken place. Once again, when T2 will be on and T1 will be off, then C2 will be charged up to plus VCC with the polarity as shown in figure. How it will be charged? Through VCC RL1 and T2. After complete charging, C2 will stop further charging. That means charging current of C2 will vanish, and C1 will start discharging. At the same time, C1 will start discharging through RB1 and T2. After complete discharge of C1, it will once again recharge with opposite polarity, and as soon as it will start charging and cross the zero value, that means VC cap 1 will charge from minus VCC to 0 towards plus VC, but as soon as it will cross 0, a positive spike will be applied across base of T1, which will force T1 to go into saturation, forcing T2 to go into cutoff. That means once again a transition of state will take place. Thus it is seen that so long C2 discharges, T2 remains cut off. So long C2 discharges, T2 remains cut off, and so long C1 discharges, T1 remains cut off. So long C1 discharges, T1 remains cut off. As soon as C2 starts charging, T2 turns on, and as soon as C1 starts charging, after complete discharge, T1 turns on. So charging in opposite direction does not take place at all, but a initial start of charging with opposite polarity causes transition of state. Initial start of charging any capacitor with opposite polarity causes transition of state. Therefore, VC1 output is given by a waveform like this. When T1 is on, VC1 equal to 0, and when during this period VC2 equal to high. When T2 is on, VC2 equal to 0, and at that time T1 becomes on. So a complete waveform is like this one. This period is T1 and this period is T2. Complete cycle equal to T1 plus T2.